Hello, my name is Devin.
And I'm Leela.
In this presentation, Leela and I will be discussing our investigation into the thermoresistive effects due to blood coagulation through a Renaissance boundary approach.
The final goal of this approach is to develop a prototype of innovative technology that offers a resolution to the learning challenge. These elements will be introduced and discussed in greater detail later in the presentation.
Moving forward, we will introduce the student learning challenge. The blood that flows through the systemic circulatory system is responsible for regulating the body temperature and oxygenating systemic tissues. The blood does this by transferring heat via convection to the surrounding tissues that vessels pervade. This line of thinking led to a thought.
A blood vessel strongly resembles an extensively insulated heat exchanger. In a heat exchanger, if the flow is decreased, the heat duty is also decreased. We also know that from clinical health science research that clotting in the vascular system decreases the blood flow to extremities in the body. An example of this might be when a diabetic is experiencing cold feet.
Even though these symptoms are not correlated to blood coagulation, blood flow is of interest in this situation. Exploring these elements in detail will warrant a scope of parameters that affect the heat transfer and fluid mechanic principles of blood. Ultimately, we arrive at the question: what are the thermoregulatory effects of blood coagulation on the human body?
To better define the student learning challenge, we continuously ask ourselves, what elements affect thermoregulation in the human body? Ultimately, this question was met by a gap in the literature, which correlated blood clotting and issues in the thermoregulatory processes carried out by the circulatory system.
Bridging this gap is our student learning challenge. To bridge such a gap, we must first make connections of the identified correlation between heat exchangers and blood vessels. To fully understand the transfer science components of the circulatory system, primary connections must be made with respect to foundational elements in heat transfer. Since the circulatory system is responsible for regulating body temperature, a justified heat transfer correlation would be to connect an artery, which is responsible for sending blood throughout the body and heating the surrounding tissues, to a heat exchange-like concept. Vessel vein blood circulation can be likened to a counterflow heat exchanger, whereas a network of blood vessels, arteries, and veins may be viewed as a convective flow of blood parallel to a thick-walled pipe, such that the tissue, fat, muscle represent insulation. The blood capillaries themselves represent the pipe, and the blood clotting represents fouling effects. When combining these connections, the principal heat transfer concept of interest is thermoresistance.
Our project timeline is outlined here. To fully develop our topic and impose a Renaissance boundary approach, we need a plan of action in which we gather information necessary to prove or disprove our hypothesis, which is that blood clotting affects thermoregulation. Once information is gathered and the appropriate student learning challenge is identified, we set off to narrow the scope of our challenge in which specific characteristics can be developed by means of the student learning challenge. This takes the face of various COMSOL models, analytical solutions, and thought experiments.
When completing a literature review to gather information about these topics through the scopes of heat transfer and fluid mechanics, we had to ask ourselves questions like, has there been research done over this topic before that could help guide us? How does the circulatory system function? And how does a heat exchanger function, especially as it relates to biological implications? And finally, what are the effects of resistance in a system? Ultimately, answering these questions will serve as implicating the knowledge acquisition paradigm of the Renaissance boundary model.
From the literature, it is found that a study like this has not been done with means to heat transfer concepts. However, there were numerous amounts of fluid mechanical approaches demonstrating clotting effect on geometrical implications and the velocity profile, as well as increases in shear stress on the blood vessel from thrombosis and coagulation.
To seek more guidance, other resources were considered.
To better understand our student learning challenge and achievability of our prototype of innovative technology, we spoke with Dr. Arce, who informed us of the important connections between modeling blood flow to heat transfer and fluid mechanical elements. He also shared insight on how to better facilitate the implication of the Renaissance boundary model into our project.
We also spoke with Dr. Jorgensen to assess complications with modeling in COMSOL to combat the necessary parameters needed to specify a system of this nature. Primarily, our COMSOL model required multiple physics components to fully describe our system, such as structural mechanics, fluid-solid interaction, pipe flow, and heat transfer in solids and fluids. Dr. Jorgensen helped resolve some of these issues. Crossing the boundary from knowledge acquisition to knowledge transfer paradigms is where we experience drawbacks and complications. The flowchart here establishes how complications presented themselves and how they were overcome. As previously mentioned, we met with Dr. Jorgensen to combat issues experienced with COMSOL as they relate to specification problems. Ultimately, this was met with developing an analytical solution to see what other information we can extract from the system. We also decided to use COMSOL's preloaded heat exchanger application to develop what information could also be extracted from this application. To circumvent complications with specifications, we constructed two simulations of the same geometry, one to analyze heat transfer concepts and the other for fluid mechanical interpretation. The results from these advancements will be discussed later in the presentation.
Quantifying and specifying all the components of the thermoregulatory system, namely determining the material properties of blood, blood vessel walls, fat, skin, etc., was required to observe the effect on thermal resistance in a general blood vessel model with only one clot at a locally fixed position. Due to the symmetry in the system, radial resistance was the ultimate specification in our COMSOL model in order to observe temperature effects. The COMSOL result will determine if our student learning challenge has potential. From COMSOL, we were able to establish a general blood vessel model with a locally fixed blood clot. To do this, it was necessary to specify all the various parameters associated with the system. These parameters were pulled from various literature journals to culminate the proper specifications. For example, we had to specify the velocity of blood, thermal conductivity of blood, heat capacity of blood, etc. Due to the cross-sectional symmetry in two dimensions, the model can be reduced to a cylindrical coordinate energy balance, in which radial geometries were the focus of this model. This simplification is met with the understanding that the resistance of a blood clot on the blood vessel system and its radial effects. As you can see from the temperature gradients present in this cross-sectional view, the blood clot imposes variation in the radial temperatures, such as we move away from the midline of the vessel, the temperature begins to decrease. Indicated by the green circle, there is a slight fluctuation in temperature that shows lower temperatures closer to the midline of the vessel than at sites where there is not clotting. I implore everyone to imagine the effect of multiple blood clots in a vessel system at various fixed locations. The temperature profile displays a cut-through of the section where clotting is present. The various circles indicated on the graph show points along the cut where a boundary layer exists. This illustrates the effect of resistance from the different elements in this model. The curvature in the graph can be explained through the extensively observed resistance in the blood clot. In summary, blood clots, like fouling in a heat exchanger, show resistance.
To combat problems with specifications, we decided to do two separate models, a heat transfer model and a fluid mechanics model. As you can see with the velocity gradients outlined in this graph, the site of the clot decreases the cross-sectional area in which blood flow occurs, which can be likened to the effects of a nozzle. However, the velocity equilibrates to a traditional laminar flow as flow moves away from the fixed location of the clot. It is important to note the implication of shear stress that is promoted from a blood clot. Again, we implore you to consider multiple clots and how these stresses affect the circulatory system. Ultimately, fluid mechanics and the concept of shear stress can be used to explain cardiac arrest. Another approach that was implicated was the use of various pipe flow equations to analytically determine the axial temperature drop along the length of a blood vessel. This will be further discussed in the following slides. However, with regards to the pre-programmed application for a heat exchanger, we could not fulfill the uses of the application due to the size of our system. Therefore, it will no longer be used or discussed in our presentation. The temperature profile was constructed from the differential equation outlined on the slide. This pipe flow equation serves as an energy balance for an arbitrary flux of heat through a blood vessel. From this temperature profile along the length of the pipe, assuming cold conditions experienced by a human, you can see the temperature drop along the length of a foot-long blood vessel is rather minute, but is likely and can explain the temperature fluctuations of the body. Ultimately, the steep slope of the plot is met by the extensive insulation due to fat, muscle, and skin. The overall heat transfer coefficient for the system is 0.046 watts per meter squared Kelvin. The heat transfer coefficient accounts for the fouling factor of cholesterol. Some other important parameters and properties are tabulated in this slide. For example, Reynolds number, Prandtl number, Nusselt number, and convective heat transfer coefficients for blood are all outlined here.
This slide notes the approaches we took to answer our student learning challenge and the respective real-world applications of our finding, and the path we took to arrive at those findings.
To discuss some of the biomimicry elements we used, biomimicry was not an element that we used to elevate our prototype of innovative technology. However, the constant comparisons and connections to pipe flow, heat exchangers, and the thermoregulatory processes constitute implied biomimicry elements.
Blood clots can be likened to fouling in a heat exchanger or in pipe flow. They cause thermal resistance and therefore a cooling effect. This could lead to methods of detecting and locating blood clots through advanced thermal detection mapping. We currently have made multiple models in COMSOL and would like to build on these to offer more useful applications and informations.
An implication of our models could be met with advanced thermal detection mapping that pinpoints sites of thermal fluctuations to help locate clotting and ultimately advance the medical field, and administering medication to treat site-specific clotting. This is our proposed prototype of innovative technology. The culmination of the work we've completed for this project would be used to develop such a device.
The following are the references that we used to develop some of the specifications for our COMSOL models.
And if you have any questions, please feel free to reach out to us via email or reply to our discussion post. Please have a wonderful evening. Thank you.